Welcome everybody to this seminar. Today we will see how to use MATLAB and parallel computing. So, a little recap on our role. As you probably know, we are the MATLAB student ambassador for Politecnico of Milan. So we are the connection between Politecnico of Milan students and Matworks. So we try to help students to solve their problem with MATLAB and Simulink with some events like this one and managing the communities online, so on Facebook and or Instagram. So let's see how today agenda. Today we will start from some theory about parallel computing. We will see how to instantiate this parallel computation on a local machine, and after that a case study using this toolbox. After that we will see how to create a remote server computing pool and use this server in a real case study. So let's start from a little bit of theory on parallel computing. If we have a big process, so an high and huge complex process, we can apply the parallel computing approach if and only if we can divide this process into sub-process, easier of course and smaller, that are completely independent one from the other. This because once we have divided this process into small process, we need to be able to compute this process independently one from the other. This can be done only if the starting process, the big one, were divided into independent process, sub-process. Once we have computed independently these different smaller processes, and we can obtain the final result summing up all of the results. Of course, it is evident that we can reduce the computational time by a factor of 4 in this particular case. But what I mean when I say independent? Actually, if I have this big process, independent means that I can compute this little portion without even knowing the results of the other portion. So as you can see here, I can take my small process and independently, without knowing anything of the other one, computing my results and obtain, of course, the final results. Let's see how to use this parallel toolbox on a local machine and why use it. The reasons are multiple, of course, but once for all is that we can reduce a lot the computational time. In particular with MATLAB and Simulink, with some small adjustment in the code, we can exploit the full potential of the machine and the code that we have written. And at the same time, if we have a cluster of computer in the cloud, we can use directly from our local machine this cluster without changing anything. Objective is that you can focus on your work of engineering without taking into account the computational time, because the computation is running offshore on an external server. Now, actually, there are lots of different procedures that you can use in your code, when you are writing your code, to improve the performance of your code without taking into account the parallelization. In fact, for example, one of the most easiest one is to pre-allocate the space without allocating it dynamically during the execution. You can see actually that MATLAB in the code analyzer show you how to improve, to make this little adjustment in order to accelerate the execution of your code. For example, in this case, it suggests you to put the semicolon to suppress the output and to use the brackets to allocate the code. So how we can run MATLAB on a multicore machine? There are two different ways. The first one is actually used by everyone without even know it, because it's simply multi-threading of the function of MATLAB. So when you execute your code normally on a modern machine that have multiple cores, MATLAB automatically turn on the multi-threading, so some of the function are actually optimized for this multi-threading and use the multi-core in order to accelerate the computation. This is implicit. You have to do nothing to enable this functionality. The second one is the parallel computing using explicit function. So What I mean is that with this specific function, the user can specify the number of workers that he wants to work on this specific task, and decide using the specific function how to parallelize the work in order to obtain the results that he prefers. This second part is the one that we want to focus it on today, because it's actually the real parallel toolbox functionality. Here you can see actually a real example of a 40,000 iteration of a Van der Poel equation. As you can see in the bottom right part, you can see a cluster of 1,000 workers, whereas a cluster of 200 workers in the top part, and the desktop, normal desktop with 20 workers. That is actually not bad, but as you can see in 2.9 minutes, the desktop completed only the 2% of its work, whereas the cluster with 1,000 workers, the 100%. So the point here is that we can compute our calculus in a shorter time in order to perform other tasks. In this case, Van der Poel equation use the parfor function, that is the for function, the classic for function, but parallelized. So what I mean parallelized, I mean that I have a for cycle that is each cycle is independent from the previous one, so I can select and use this parfor in order to compute the different iteration in parallel, reducing of course a lot of the time of computation. There are different type of parallel integration in MATLAB, from easy to use one, so the immediate one, to the more personalized one that of course are harder to use. If you turn on the use parallel functionality, you simply stating that using the specific function like parfor, batch, and so on, you are using a different worker in your machine. Actually, you can go deeper, and with some more specific function like spmd and create job and so on, decide which job must be sent to which worker. And so you can have the control of the specific task to the specific processor, to the specific worker that you want to execute. Of course, this one is more advanced, because next it requires that you know and you understand how to better divide your work in order to obtain the best performance. So let's see the example of parfor. For example, we have a parameter sweep, like for example a Monte Carlo simulation, and the point, as I said before, is that we need to have no dependency between the different tasks that we are executing. So for example, here we have a MATLAB client, the rectangle, the orange rectangle are the tasks that we have to perform. As you can see, if we perform them sequentially, we take some times. If we split this task into 3 workers, for example, that execute in parallel, we reduce the amount of time. As you can see, the difference between for and parfor is not so much. In fact, for and parfor are the syntax is the same. The only difference is that you need to be sure that this function, in this case my function, is a function that is independent completely from the previous execution of for. Otherwise, you will see an error, of course, during your execution, because, for example, the second worker need a result of the previous of the other worker, and this, of course, is not possible. So let's see, for example, parfor loops, how it works with multiple workers. It allocates dynamically the work during its computation. So, for example, here we enable parfor. As you can see, we have worker of different size. In this case, 4 workers. We have 10 iteration. At the starting point, MATLAB allocate and divide this iteration in different groups based on the potentiality of the different workers. And it starts allocating some iteration to the single worker, as you can see. For example, the worker in the top right corner take only 1 iteration because MATLAB see that, for example, is smaller, have lower computational power. So it start, worker 1 already finished, so MATLAB assign to it another iteration automatically. The other worker finish, and the remaining iteration are assigned to the worker that have already finished. In this way, we optimize the time of computation. Finally, we have our parfor that has been executed by the 4 different workers in shorter times. There are other applications of parallel computing toolbox in MATLAB. One is parsim. Parsim is the parallel simulation of a Simulink model, of course. The objective is the same as parfor, so the objective is to reduce the computational time, and the concept is the same. So using different workers that simulate different tasks, we can, for example, make a sweep of parameter in a Simulink model and see the different results, how it compares, without taking too much time. Now I give the word to my colleague Alberto that will show you some real case study on how to use this parallel toolbox in your code.
Okay, thanks Daniele, and now let's move on to some case study. Okay, first of all, our first case study is the most simple one. We would like to see the optimization of the for loops. In particular, we will have the first one, that is the classic one with for and nothing optimized, and the second one that will have parfor. But to better show you this, let's move on MATLAB. First of all, let's look at the toolstrip parallel. If you go here in Home and then you click Parallel, you can find, first of all, what parallel is active now, my local parallel. Then you can discover new clusters if you have some active one, or you can create or manage your cluster. Let's look at these windows. Okay, you can find that the properties of the local cluster, and you can validate your cluster by checking if your computer can do and perform this type of operation. So if you click validate, the computer starts processing, and it will check these categories in order to be sure that your device, your computer, can handle this type of work. Okay, giving some minutes to this, it can process all this information. Once the job is concluded, so we validate our pool, we can select, and we can see that we have different information here about the number of workers we have for the different stage. So if I have to perform a SPMD job, I have 4 workers, the same for the other 2. Okay, very good. If I go here in parallel and I click on monitor jobs, I can open this window here that can give me the information about the current status of my parallel pool. Now, currently, I have no pool open. Moving on the code. Now I would like to show you the comparison, as I explained, about the unoptimized and optimized code. So first of all, let's run this first part. It will take some seconds, but with the function TikTok, I can be sure to say the correct time required for this type of function. Now it's working. Let's wait some seconds. Okay, it takes 34 seconds. Very good. Okay, it's not a fast operation. I mean, it's quite intensive, but we have, let's say, a score, a time to compare with. Okay, moving on, I can clear all, first of all, to be sure that all the steps are the same. Okay, and then I can run some code. Let's start, and I will explain this. Okay, clear all, you know exactly what it does. Now, TikTok, take the time, and we select here parpool. What is parpool? It's one of the 3 types of initialization of the parallel pool. The first one, parpool, is the explicit way. I can write parpool, so I'm saying to the code and to the PC to start initialize the parallelization pool. Okay, and this is the explicit way. The second way is an implicit way. I can call a function, parfor, for example, that requires the parallel pool. Okay, this will start the pool by itself, so it will initialize the pool. Meanwhile, the code is running. So if I arrive to a parpool, parfor, and I don't have a pool already working, it will initialize a new one. Third option, if I have to start a pool, I can go down in the left corner on the symbol here, and I can click here, start a parallel pool. Now it's shut down because it's already running, but is, let's say, specular. Okay, and what I can see is that I have initialized the pool that required 39 seconds. Okay, it's let's say it takes some time, okay, but the benefits are, let's say, quite important. In fact, if I go to and see how many seconds take the parfor operation, it will take 13 seconds. You may wonder why I have to start a parpool and do this if the normal operation is faster if I sum the two times. Because if I have to redo this operation, okay, it will not start again a parpool, but it's already running, so I can take less time. Again, probably is sometimes comparable with the last execution. In fact, 13 seconds again. Perfect. Last thing I have to mention to you about the parallelization parpool is that if you want to run this type of command on your PC, you have to consider that is quite hardware intensive. So you must have on your PC at least a multicore processor on which each core can become a worker. Second of all, you must need also some gigs of RAM. In particular, you need 2 gigs, at least 2 gigs for each worker if you are using a MATLAB operation, and at least 4 gigs for worker if you are using a Simulink parallelization. Okay, so you need some high performance in order to run, to have really true performance and benefits by using the parallelization. Also, keep in mind that if you split your works in different, let's say, operation, you need, let's say, some temporary file in order to save the execution of part of this code in order to get the information once you complete all the part and stick together and give the out result. Okay, now let's move back to the presentation and let's see another example. Now I would like to show you the capability of scaling up in multiple core, also with the simulation. In particular, I would like to share with you the heat thermal of an house. In particular, we will set different value of the set point. So the let's say what you do with the with your knob on the thermostat of your home, and so we will see the different response of the thermal exchange of your house respect to that. In particular, again, this is a simulation that mixes the capability of parallel computing and also Simulink. So we will run multiple simulation, multiple Simulink instances in parallel in order to see what is the response. Okay, now let's move back on MATLAB. Okay, we don't no longer need this. Okay. Yes. Okay. And in MATLAB, we can see now the script that, first of all, let's clean up our mess here. Okay, first of all, the first row define the set point of our simulation. So we will start from 55 degree Fahrenheit up to 95. So we will have a quite significant number of set point. Now we can load some side variables. Okay, and now we will launch the parsim. Notice then I have already prepared here the Simulink file. In particular, we have here the set point, the conversion from Fahrenheit to Celsius, and the overall system. Of course, this is a quite complex system with the heater simulator with some transfer function, and the house. So again, here we will have some transfer function of the house environment. In particular, what I want to point out is that here with this approach you can use whatever simulation you want, and this is very important if you have to compare lots of different simulation. Okay, let's run the script. What's pop up is this window here. Now, as you can see, it's initializing the parallel pool, so it will take some time. And here also we have this fancy and beautiful representation of our simulation. In particular, below this taskbar, we see lots of dots. This is the set point we just implemented, so starting from 55th up to 95. Okay. Again, it takes some time because it has to initialize each worker, each core, and send to them and point to them the correct simulation part of our experiment. By the way, now should have finished. Okay. Again, it depends also on the power of your machine. My computer now have 4 workers. If you have a very powerful machine, multi-thread, it can instantiate up to, I don't know, 64, 32, 64 cores. And you can see here there's the procedure. Okay, it already ended up. At the end, it cleared the compute pool. Okay, we have finished the simulation. What we can do now is to plot this result. So in MATLAB, I can write a plot of out, that is the output of our simulation. Now I would like to show you the output. Here we are. Okay, we have now all our runs here. Okay, and we would like to compare the heat cost. In particular, this is with the slow or the lowest set point, so 55th degree Fahrenheit, and we can compare the different behavior. Of course, you can select the different test, and you can go down, blah 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 blah, until your most high value. And as you can see here, this is the heat cost. Of course, it goes like crazy, and this is the other examples. Okay, for this part of of demo, it's finished. Let's move back on the presentation. Okay. I would like now to introduce to you the capability of scale up the computation and to perform parallel computing also on computing pool. What does it mean? Okay, since now you use the local PC, but nowadays with the capability to connect to the network, we can connect to internet and use some provider services like Amazon Web Service in order to use their computer capability in order to do our task. In particular, we can send the information, the jobs, and get back the results. Okay, how to do this? First of all, let's look at the advantages. The offload computation can free up your desktop and can allow you to access to better computers. So you will not stress your local PC, but you will use some servers anyway around. And also, these servers are dedicated for computation, so probably they can handle better your workload. Second, this specific computer cluster will use more cores, so they will parallelize better, and also they can shrink down the time required for the simulation by some considerable amount. And then also it can scale up the memory. This is important because if you have a big data set with lots of information, if you have a local PC with a quantity of memory that is limited, it cannot compute and get the best from the parallelization. If the away PC, so the remote computer server, have lots of RAM, it will for sure parallelize better the workload. Of course, with the MATLAB client here that define the work, the script and what must be computed, you can select the type of work you want and you send it to the cluster. And then in the cluster, each core of this away machine can work on your job. So it will scale up and use as many resources as needed. Okay. In order to show this, also you have to figure out that all these things are done in the cloud. So you will not use your local network or your local machine. Now let's move on to the case study. But to do this, I give the word to my colleague Daniele.
Thank you, Alberto. So let's see some hardware requirements that you will need if you want to use this toolbox. First of all, MATLAB suggests to use a maximum of one worker per physical core that you have on your machine. So if you have a quad-core processor, you can have a maximum of 4 workers running together. About the RAM, MATLAB requires plus 2 gigabit per MATLAB worker, whereas if you want to run multiple simulation in parallel, you will need 4 gigabyte per each Simulink worker. Last, memory. About the memory, you will need at least 5 gigabyte in order to store data directories for the parallel computing. If you want to use the GPU for parallel computation, we know that the GPU in particular have an architecture that is particularly suitable for this type of computation. The only one compatible is the standard for parallel computing, that is the CUDA NVIDIA GPU. So you will need a CUDA-enabled NVIDIA GPU in order to parallelize the calculus on the GPU. So let's see this final demo. This final demo have both a part where we will use a parallel on a local machine and a parallel on the cluster online. So let's start from the first script. As you can see, this demo want to compute the Van der Poel equation. This first part of the code start with eliminating all of the previous parallel works that we have already created, and create a new parpool, so a new pool of workers in the local machine in order to be used with this demo. So let's run this first code. So it is switching off the previous parallel pool, and it is starting here in the left bottom side. You can see these 4 lines that indicate the starting up of the parallel computation on the local. It takes some minutes. Okay, so it's started with the 4 workers. I have 4 core on my machine. Now I make an interactive run on this local machine. So I run this section. It takes some time because it's actually a high complex calculus. For this reason, we have selected this example today for today's seminar. Okay, let's wait. As you can see here, I have get munu is the function. Param sweep parfor is the sweep of the parameter that is actually taking so much and is actually computing the calculus using the 4 workers that I have created. As you can see here, I can see that the time elapsed is 38 seconds. That is quite a lot. And I can visualize the surf that is belonging from this calculus. Now, I can do the same thing using this cluster. This is a cluster that we have created in order to perform this demo. Is a 36 worker cluster. As you can see, I can start up my cluster. In this case, it's already running, so this code is actually only trying to start up the cluster if it is not starting. And after that, I can start my computation on the cluster using, in this case, 18 worker. As you can see, we are simply creating the cluster and starting up it on the server. So I run this section. It is switching off my local cluster, and it is starting on a parallel pool on this server. It takes some time. Of course, the interesting thing is that this cluster could be used from different users that are working, for example, on the same project with only one machine that is useful for all of the team. Okay, perfect. Now, as you can see from the script, I can see that I'm connected to the parallel pool with 18 parallel workers. And I'm starting reporting the host computer. Now, I can execute the same calculus than before. As you can note, is the same exactly of before, but now I'm running it on the parallel cluster. So we can run this section. It's computing the same calculus, but of course with a number of workers that is higher. As you can see, we are transferring file to workers, and the time elapsed is 13 seconds. What does it mean? We have 1/3 of the time of computation than my local PC. So that's the aim. That's the powerfulness of this solution that can actually help in computing this high requesting calculus without even touching the performance of the machine, because his key point is that now this calculus take 13 seconds is not so much, but let's suppose that I have a calculus that take some hours, okay, but I need to work with my machine on other tasks. With this method, I can send simply the task to the cluster of machine that is completely autonomous, and so it is working without touching the performance of my machine. So I hope that this seminar has been useful for you to understand the potentiality of this toolbox, the parallel toolbox. And now, if you have any question, feel free to ask, of course, on our channels, on Facebook, Instagram, and email, but most important, to the roundtable that there will be at the end of this meeting on WebEx. You can find the link in the description below. I hope that all of you can participate and ask us questions to discuss about this toolbox. Thank you for your participation and have a nice day.